Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working on problem number 3.33 from Elementary Principles of Chemical Processes, 3rd edition. The problem statement says, a storage tank containing oil with a certain density is 10 meters high and 16 meters in diameter. The tank is closed, but the amount of oil it contains can be determined from the gauge pressure at the bottom. Part A. A pressure gauge connected to the bottom of the tank was calibrated with the top of the tank open to the atmosphere. The calibration curve is a plot of height of oil, H, in meters, versus P, gauge pressure, in kilopascals. Sketch the expected shape of this plot. What height of oil would lead to a gauge reading of 68 kilopascals? What would be the mass, in kilograms, of oil in the tank corresponding to this height? So I've got here a diagram, and let's walk through the diagram. So they told us that the oil has a certain density, and so I wrote that down there, that has a certain height, it's 10 meters tall, and it also has a certain diameter. We know that oil goes into this tank and oil comes out of this tank, and this is sort of a holding spot for the oil. When it was calibrated, it was open to the atmosphere, which I also assume that it means that the oil, that the tank was empty when they calibrated it. So the pressure gauge, when the pressure gauge is reading 0, that means we're at atmospheric pressure. The oil has a certain height, which is H, and that's measured by the pressure gauge that's connected to the very bottom of the tank. Now, in real life, you couldn't really connect a pressure gauge to the very bottom of the tank unless the tank was like sitting up off the ground or something like that. So the pressure gauge would normally be like somewhere close to the bottom of the tank, and then when you calibrated it, you would account for the amount of height the pressure gauge was up off the bottom of the tank. The other thing that you'd want to pay attention to in some of these processes is that you don't want whatever this head is contained in this head space, you don't want that to get sucked out with the outgoing pipe. So let's say that this line is not close to the bottom of the tank. Let's say it's right here on the middle of the tank. Well, if you let the oil level drop too low, sometimes you can suck air out or suck whatever that atmosphere is above the tank out along with the oil. You can froth up the oil or something like that, and it's not good for, maybe it's potentially not good for your process. Anyway, that's some industry stuff for you guys. It doesn't really pertain to the problem very much, but it kind of contextualizes the problem of why you need to know where the tank level is. Okay, so let's get into part A. They asked for 3 things here. First, they said sketch the calibration curve, and then they said find out what the height of the oil is and estimate how much mass that oil is. Okay, so this function describes the height of the tank and the pressure relationship. You have a certain calibration pressure that you're setting, so there's a certain amount of pressure you can add or take away. It just depends on where your pressure reference is. So that's what P naught is, it's a pressure reference. And then you have the behavior here, which is your density times the height of the liquid times the acceleration due to gravity. And then that equals the total pressure in the tank, or according to the pressure gauge at the bottom. So if we calibrated on atmosphere, then we can assume that we're set at 0. Our gauge pressure is perfectly lined up with whatever the atmosphere was, and so now we have gauge pressure of 0 when the tank is empty. The pressure gauge reads 0. Okay? So that means that our line here goes through the origin, and it has a positive slope with respect to height because it's directly proportional to the height the pressure gauge is. It's just a line. And this would be what the function looks like if our reference pressure is 0. Okay, so we can turn this into an empirical relationship where we've got our pressure in kilopascals. Well, then we can combine our density and gravity terms together to just form an empirical number that has a unit of kilopascals over meters, and then when we multiply the tank height by that, we'll get a certain pressure in kilopascals. Okay, so that's what we do here. We have our density, we have our acceleration due to gravity, and then we convert to kilopascals, and we're left with kilopascals per meter, and then we multiply that by h, and that equals the pressure. Combine all these together, and we get this relationship. And then they said, what's the height of the tank when the pressure reading is 68? Then you would just say 68 divided by that empirical constant, and you get 7.54 meters. Okay? Now they said, how much mass is that? Well, we know mass of oil is equal to density of oil times the volume of the oil. We know the volume of the oil is equal to the area of the base of the tank times the height of the oil. And we just calculate what the height was, so the area of the base is pi r squared, or pi times density squared divided by 4. So pi times density squared divided by 4, that's the area, or that's the volume, times the height is the volume, times the density. Okay, then we multiply all that out, and we get that the total mass is 87,000 kilograms. Okay. Now part B, it says, an operator observes that the pressure gauge reading is 68 kilopascals and notes the corresponding liquid height from the calibration curve. What he did not know was that the absolute pressure above the liquid surface in the tank was 115 kilopascals when he read the gauge. What is the actual height of the oil? Assume atmospheric pressure is 101 kilopascals. Okay, so they're saying, okay, we have this relationship. We assumed that in the first case that PO was equal to 0, that our head pressure of air above the tank was exactly equal to the atmosphere because it was open to the atmosphere when we did our calibration. However, since then we've closed off the tank, and now the tank has a certain gas headspace above, and that gas headspace is pressurized above atmosphere. So that's going to make the pressure in the tank seem artificially higher than what it actually is, just due to the liquid. So this pressure is actually higher than what it should be, and so when we run our calibration and we subtract off our atmosphere off of that, we actually end up with a little bit of extra pressure that's affecting our system. Okay, so we need to make sure we add that extra pressure that's in our system to our P naught term. So instead of P naught being 0, now our P naught reference pressure is a little bit higher than what it should be actually. And so that adjusts our equation a little bit, and now we solve for the new height with a pressure of 68, and that should lead to a smaller level of oil. So if you have a higher pressure in the tank artificially there because you have a higher head pressure due to the gas, and it's higher than what you calibrated on, then your liquid level is actually going to be lower because that extra pressure isn't coming from extra oil. The extra pressure is coming from extra gas. So it's kind of throwing off your empirical equation a little bit that you were using before. So this empirical equation that we calibrated on that gave us 7.5 is actually reading a little bit too high because of the head pressure in the tank due to the gas. So this pressure is, or this height of liquid is actually lower. And remember I said at the beginning that if that level drops too low, you could end up sucking out some of that extra head pressure gas in there. So if that pressure builds up too much of gas, then you'll end up sending gas out with your outlet because that level will artificially drop too low. And depending on your process, that could cause problems down the line. All right. Well, that is it with a little bit extra for you guys for problem number 3.33. I did this style a little bit different where I had everything kind of written out beforehand. Let me know in the comments if you guys prefer this kind of style or if you prefer watching me walk through the problem. Yeah, let me know either way, and you guys vote on it, and then we can stick with the style that most of you guys like. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.